Everyone to the
sorry.
office hour session with Danielle as we go about auditing Spartan-ECDSA. So Daniel, welcome, and I guess I'll hand the mic over to you. We'll go over the quiz first, and then we'll take specific questions about it, and then general questions about the audit in general. So welcome, and the mic is yours.
Thank you. So yeah, to start with the answers. So we have 6 questions in total, 3 for each session. And to start from the basic one from the first session, the question is, how many complete additions are used in the optimized double and add algorithm implemented in multiplication.circom? So the answer is 3. So we use 3 complete additions in our optimized double and add algorithm. You can see that it is in the 3 by checking this for loop. This for loop does the complete additions here, and it is executed 3 times. The number 3 comes from the comes from the fact that you can, so in total we do, let's see, so we have, in total we do 256 additions, but we can use incomplete additions for the first 253 additions because we know that the no edge case will happen in that first set of additions. But for the last 3 rounds, last 3 additions, we need to do complete addition because we might encounter edge cases. So the answer is 3. And feel free to interrupt if you have any questions, and I'll go to the next one.
There's a question in the chat, Daniel, that's from Oba. He says, on line 82, is there another complete addition?
Add complete line 82. Actually, there's one at line 89. So maybe also these are just complete additions. How many complete additions? Yeah, maybe the question was a little ambiguous. Yeah, I guess this was my bad. So if you answered either 3 or 6, I guess, or 7, that would be correct. Yeah, the question was a little bit ambiguous. I meant to, I meant to ask how many rounds we need to do, how many rounds we need to use complete additions, but yeah, so 7 is correct as well. Okay, so the next question, what are the base field and scalar field orders of the SEC Q256 256K1 LP curve are? The answers are the base field order is this, and the scalar field order is this. You can just Google the scalar field, the orders of this curve. But the key here is that the sec Q curve is a curve that forms a cycle with the sec P curve. So if you go to the if you get the information, if you get the basic parameters of the sec P curve, for example, in this website. So yeah, when you look at, when you go through this, you can see that you'll learn that the base field of sec P is this, and then the scalar field of sec P is this. So the sec Q, the cycle of sec P, will have the the scalar field order of sec P as its base field order. So the P and N here will be switched. So with that information, you can get answers. You can get these answers. Third question, we have an insecure implementation of efficient ECDSA. The verifier only checks that the proof pi is valid and does not check if T and U were computed correctly. Let's say you are an adversary and want to convince this insecure verifier that you can generate a valid signature. How would you set T and U to generate proof pi? So the answer would be, maybe we can recall how efficient ECDSA works first. Efficient ECDSA, the proof pi proves in the zero knowledge in a ZK snark this equality, and the values T and U are calculated outside of the circuit as defined here, and S is the S part of the ECDSA signature. So in a valid, correct, efficient ECDSA verification, the verifier needs to check that T and U are correctly computed as described here. But our assumption, the question says that the verifier does not check T and U and it is insecure. So how would we compute T and U to fool the verifier to create a fake proof? The answer is we can simply choose a random S in T, and then since we have this U group element here, we can just randomly arbitrarily choose these value, and we can simply adjust use as U as a group element that adjusts the answer, and then set that to be public key minus this S times T, and then we'll get the values STU that values TU that passes the check. Okay, so going to the next session, 3 questions in session 2 about our implementation of the Poseidon hash function. The first question is, how many rounds does the Poseidon instance in Spartan-ECDSA execute? The answer is 8. We can see that we can confirm that in the repo. So if you know how all of these parameters are set, you can just see this value, and the number of full rounds are 8. You can also go to, if you wanted to confirm that RF is indeed the number of rounds, you could go through the code. I don't think I can find where it is, so I won't go through it now. But you can go through the code and then check out how many rounds it actually execute. So the answer is 8. The second question, we want to build an RT8 Merkle tree that uses Poseidon. According to the specification of Neptune, what should the domain tag of the Poseidon hash function be? So let me see if I can find the Neptune place where it mentions it. Or yep. Yes, so when you go through the Neptune specification, you can see that the domain tag is defined as this one, and the question says that, let me go back to the question. We want to build an RT8 Merkle tree. So between these cases, or cases, this one, the upper one, we want to create a Poseidon hash for Merkle tree, and our RT is 8. So the tag will be 2 to the power of 8 minus 1, which is 255. If you also went to the site and implementation in Spartan-ECDSA, I believe you could find the code that computed the domain tag, and I think there was a comment describing how the domain tag is calculated. So if you read the site and implementation in our repo, then you might have been able to guess the domain tag for this question as well. The final question, confirm that the following parameters are secure. You can check that these parameters are secure or not by using this Sage script. And let me see if I can run it right now. So you can use this website to execute any Sage script. So first we can run the parameters used in our implementation in Spartan-ECDSA. Oops. Never seen that before. Oh, that's unfortunate. Okay. Okay, I think we need to skip this one. So if you just set all the parameters defined here as in this C script, so you can check the definitions of all of these variables in the in the spec, and then know which to set which. So the security level here is M, state size 3, exponent is 5, is A or alpha, and the field modulus is this thing, which is P. Okay, so yeah, thanks for a comment. So returned all true for you. I believe so. Okay, it's back. Sage math is back. But yeah, if you wanted to double check, you can run this script in the website and then see if it's secure. Okay, I hope those questions were good exercises to understand Spartan the repo deeply, and then to understand the components used in Spartan-ECDSA better. Let me know if you have any questions regarding the quizzes or anything related to the audit or the repo. Thank you.
In the third question, Daniel, of session 1 quizzes regarding T and U, what would be the case against actually constraining them in circuit, thereby saving gas on verification cost on chain?
On-chain verification is actually not practical. So on-chain, we have a like bunch of blockchain, a bunch of layer 2s now, but let's say we want to verify them on an EVM chain, like Ethereum L1 or some ZK EVM. Ethereum EVM doesn't support a precompile to do SecB elliptic curve operations. So so here actually say, so when you want to check these two equations, you'll need to do a scalar multiplication here and another scalar multiplication here. So if it is not practical to do it on chain, you have to do it off chain, and it is meant to be done off chain. So anyone can just check it in their just fetch all the proof and just check it locally, or trust the server that it checked the proof correctly.
So right now, if someone is integrating Spartan ECDSA, what verification options do they have?
They can, so we recently launched a product that uses Spartan-ECDSA. And what we do is when a proof is submitted to our server, so we store all these proofs in our server, in our database. And when the proof is submitted, we just check it, we just verify everything is correct. So we do all of these three steps to check if the proof is correct. And then if it's correct, we store it in our database as a correct proof, and then let anyone verify, let anyone fetch the proof, and then check if the proof is correct. So we don't provide a concrete concrete verifier per se, but in the Spartan ECDC library, there is we provide a TypeScript library, and there is a method you can call to run this verification procedure. So in the library, you can there is a method to verify this one, to do exactly this.
Right. So what would be the case against constraining them TNU in circuit, basically, if someone wants to actually, create a verifier on chain?
Yeah, that would be actually there are some projects doing that. I think they forked Spartan-ECDSA or some of our previous work, and they created an on-chain verifier, and that would totally work, and that will totally make sense. But that means that you'll have more constraints in your circuit, leading to a longer proving time. So there's a trade-off between on-chain verifiability and proving time. So if you don't care about on-chain verification, you probably want to offload TNU from the circuit. But if you want to do on-chain verification, then you can just include this in the circuit as well. So yeah, great question. Hope that answers the question.
Yeah, that makes a lot of sense. I can imagine if there is a P2P application that is making use of Spartan ECDSA, they don't really need to constrain this. They can, as you said, they can trustlessly check on the server that it was computed correctly, like the peers on the network, for example. But then if someone wants to use it as part of an, like the dApp needs an on-chain component, then they would have to incur those additional constraining costs, I guess.
Exactly. Yeah, great elaboration. So there's one question in the chat about the SBox exponent on the security level. So yeah, this is actually a pretty deep topic when if we want to talk about it and talk the reasoning of what the exponent should be. If you read the original Poseidon paper, I think they have the exact reasoning of why should the exponent be the one they specify. Exponent is usually 3, 5, or something else. But yeah, I don't think I can answer it right now. But if you're curious, I will direct you to the original Poseidon paper.
The 8 rounds of Poseidon, Daniel, could you elaborate on that? Why 8 exactly?
Right. So actually, that is also a parameter that is defined in the Poseidon paper. And I think, yeah, so the number of rounds is generated. So we generate a safe parameter and using a script provided by I believe, the original Poseidon authors. So yeah, they provide this Sage script. So you just run this, and then you get the parameters that you want. You get the safe parameters that you want. So the number 8 for the number of full rounds, that's the result of all of this.
And this is typically a parameter for all hash functions, right? The number of rounds.
Yes, usually hash functions have like their security defined by how many rounds of permutation they do, and yeah, for algebraic hash functions like Poseidon, they're usually exponents or s boxes, I believe. So yeah, those kind of things define the security of the hash function.
Parsley is asking, is it 4 rounds first and then 56 half rounds followed by
Yes.
4?
Yes,
Okay.
exactly. So we do half the full rounds first and do all of the half rounds, partial rounds, and then do the rest of the full rounds after that.
Maybe we can ask the fellows, do you guys know why Poseidon is ZK friendly? Why is it circuit friendly, I should say? Does anyone know?
Yeah, that's a good question.
Yeah, maybe we'll leave that as an exercise for you guys later, just something to think about.
So there's another question about if you're looking for the optimizations as well as looking for issues. For now, I believe the scope is to look for issues and try to break the thing. But yeah, if you have any suggestions on optimizations, or if you figure out any ways to do any like refactoring work or cleanup work, then I think that'll be nice as well. I'm not sure if that can be added to the report, but yeah, we can definitely discuss about it as well. Yeah, I'll welcome those kind of suggestions. Totally welcome those kind of suggestions as well.
Okay, I think that's it. So hopefully you guys are you fully understand everything. So that's good to know. I at least I hope. And thank you, Daniel, again for the great questions. The quiz was very stimulating. And yeah, we will hopefully get 1 or 2 speakers next week, maybe. Potentially about MSM and potentially about ECNE, the tool from 0xPark, trying to hunt down the author there. So yeah, and then we will conclude by the session on the 5th, where you go, just like we did last time, you go over highlights of your report and you get feedback from Daniel, and then we conclude. So thanks, Daniel. Thanks, everyone, and we will see you on Discord.
Thank you very much.